we're going to talk about the universe in 20 minutes. So it's a little bit of a task. So what's really amazing, Carl Sagan once said that we're star stuff, and this is absolutely true. We're all made of stars, but it's much more exciting than that. We're all made of the Big Bang itself. There's hydrogen and helium, which was left over from the Big Bang. And for instance, if you've ever played with a children's balloon at a party where there's helium in the balloon, the helium in the balloon, believe it or not, was formed in the first 3 minutes of the Big Bang itself. What's even more astonishing than that, of course, we are all made of elements like carbon, and which is in almost all the molecules in our body. We're made of calcium in our bones, iron in our blood. These are all the products of stellar evolution, and in the heaviest cases of things like iron, those are formed in exploding stars, supernovae. And we are all the product of something like 1,000 generations of stars. And over that 1,000 generations of stars, each of us is the product of something like millions of stars. There's millions of stars, the atoms of millions of stars are in each of our bodies. So it takes an entire village to raise a child, but it takes a galaxy over an entire cosmic history to form the village in the first place. So we're going to talk about this, and to get started with, in the first part, I'll talk about our place in the universe, what we've learned about the evolution of the universe in the last couple of decades in particular. And the second part, I'll talk a little bit more about the puzzle that we've been working on, which is the puzzle of exploding stars. And in the epilogue, I'll sort of tie it all together. Imagine that the sun lives not over 11 billion years, that's a long time. So we'll say 100 years, like a human. Every year of the star's evolution, like our sun, if it's 100 years of lifespan, is something like 300,000 years. Every second is like 3 years. The sun right today is about 45 in that sort of age span, a middle-aged star. And you can see it's about here at this point in the movie. As it ages, it's getting brighter. In fact, it's about 20% brighter now than it was when it formed. And over the next billion years or so, maybe 10 years in that sort of stellar evolution, it will become so bright that water on the Earth becomes evaporated. Life on the Earth will become pretty difficult. But on timescales even longer than that, about 90 years in this sort of stellar age span, it's going to become a red giant. And over that red giant phase, it becomes 100 times brighter than what it is today. It starts to become larger than the Earth's orbit. And you can see that here. Then it undergoes another phase of evolution. And in that later phase of evolution, it becomes a type of variable star. And you can kind of see it in this photo, it's kind of pulsating. That's called an RR-Lyra variable. Again, about 100 times brighter than the sun, where it starts to burn helium. And eventually, it'll become a dead cinder of a star. And that, as you can see at the beginning, that dead cinder, that compact object, is called a white dwarf. Now, a white dwarf is kind of an interesting object. Sometimes we say it's a dead star. Maybe retired star is a little bit better analogy to use, because even though it's sort of finished its lifespan as a regular burning star, where it burns nuclear fuel, it goes into this later stage of evolution where it draws off of its account of energy, of thermal energy that's within it, and it slowly radiates that away over a time scale greater than the age of the universe. So it becomes a cooling white dwarf that is supported against gravity. What can happen sometimes, and this is one of the great mysteries we'll be talking about today, is that those white dwarfs, about 1 per every 100 of them, can explode as a supernova. This one here went off in 1994. There's the fourth one that went off in 1994, so it's called 94D. The supernovae are named alphabetically. So 94D went off, and you can see here in this image, it's as bright as the entire brightness of an entire galaxy combined. So typical galaxy has about 100 billion stars. So that single supernovae is as bright as about 100 billion stars combined. And it's an amazing object. You can see them over the clear expanse of the cosmos. Now, what's really remarkable about these type of supernovae, they're sometimes called thermonuclear supernova, an explosion of a white dwarf that's driven by the energy of the burning itself is that they can be used to measure distances in the cosmos. So that was one of the most amazing breakthroughs in cosmology. But let me just explain a little bit, take a step back. What do we actually mean here? Well, space is expanding. This is an artist's rendition. So you can see here, imagine space. Space-time is curved, according to Einstein, and the mass-energy distribution of the universe tells space-time how to curve, and then that space-time curvature tells mass how to move. So in the universe is basically, it can only expand or contract. It's almost impossible for it to sit still. So space is expanding, and here you can see in this movie that the distance between galaxies increases over time. So that rate of expansion tells us something very important about the composition of the universe. Now, this is a very confusing idea, I think even sometimes for scientists to sort of get their head around. Sometimes people ask, you know, if space is expanding, does that mean like my house is expanding? Can I just wait and get a extra bedroom in my house? No, it doesn't work quite that way. Like the galaxies in this image, they stay the same size. Atoms stay the same size. Everything that's bound together by forces other than gravity stays the same size. And the galaxies, which are bound by gravity, are not influenced by this large scale structure of space-time. And it's not like an Alice in Wonderland like effect either, where we're getting smaller and the universe is getting bigger. We know that because the atoms themselves have a specific fingerprint. When you look at distant galaxies, you can measure their light, and the atoms are not changing. So it's not like an Alice in Wonderland effect where we're getting smaller and the universe is getting bigger. The universe is getting bigger, we're staying the same size. Now, when scientists first looked at these distant galaxies to measure the expansion rate of the universe and to measure distances, what they expected to see was something like this. Here is the Earth on the lower right, and in the upper left, let's say, is a distant galaxy. So space has expanded, and the galaxy is moving away from us, and you can measure that distance. But it turns out, so the light comes out, we would measure that. When scientists actually went in the late 90s to measure the distances to these galaxies, instead of that, which was expected, they saw something a little bit more like this. So this is the expected, it's according to what you expect in a simple model of the universe, let's say, that's just made of stuff like us, atoms, as well as other matter that's called dark matter. Include all that, you get something to look on the lower left. But instead, space is bigger than that. It's larger. That means that the galaxies that we're seeing and the supernovae in them were dimmer than what you would expect otherwise. So more distant supernovae, dimmer supernovae, could only be explained, it turned out, by the existence of an additional kind of energy, which is called dark energy. And dark energy is a very strange kind of energy because it expands space, and it repels space, whereas ordinary matter and even dark matter causes space-time to contract. So, in fact, it was impossible to explain these distant supernovae with just the existence of ordinary matter and even dark matter. And that led to the idea of dark energy and the idea that the universe is not only expanding, but it's actually accelerating in its rate of expansion. Should be met with intense skepticism, and it was. And it turned out, over time, it was independently verified through several other methods. So this is a picture of the cosmos as a whole. And so to guide you here, going up on this image is time, and space is kind of represented pictorially on the horizontal axis. So we are somewhere in the middle of this image. And what you can see is that as time evolves, space is actually evolving to be expanding at an ever-accelerating rate. This really dramatically changes our picture of what the universe is like. We used to think that if you would wait long enough, you could see the entire universe. We can't see it all today. It's a big place. And because there's a beginning to time, the Big Bang, you can't see it all. But in fact, the picture is much changed with this idea of dark energy. Because with dark energy, the universe is accelerating. And in fact, today we see almost everything that we are going to see in the universe. There's a kind of distant curtain, if you will, not a real curtain, but a sort of curtain that curtails what we can see just due to the fact that there was a finite beginning to time. That's called our horizon. and our horizon is about as big as it's ever going to get. It's going to get a little bit bigger, but not by that much. And eventually, actually, like cosmic actors, the galaxies are going to move beyond the curtain, and distant generations, billions of years in the future, will actually see less of the cosmos than we do today. That's really a fundamentally insightful breakthrough that came of this. So that was part one. There's a great mystery here. And the mystery is intrinsically tied into this mystery of what these supernovae are. Because actually, there's a great secret here, and that is that nobody actually knows what these supernovae truly are. So let me tell you a little bit more about that. There's a white dwarf in this image. It's in the lower left. And the basic picture when I started in this field and that people sort of believed in was that you could take this white dwarf, and this white dwarf has, it turns out, an intrinsic mass limit, about a little bit less than 1.5 times the mass of our sun, about 1.4 times the mass of our sun. And if you brought that white dwarf up to that mass limit, something would happen and it would explode. And as it explodes, because it has about that same mass, no matter where it is in the universe, it would have about the same brightness. And that was a story that everyone told and everyone believed. So we did some simulations of this. So let me tell you a little bit more about what goes on in those simulations. We have these massive supercomputers, some of the biggest computers in the world that we use. And the computers are very important. They're growing very quickly. We put fancy math. This is my fancy math. Fancy math goes into the computers, and there's a lot of sophistication and algorithms that go into this. My colleagues like Sigal Gottlieb and our colleagues in the math department are experts in this. But there's an important side to this too, and that's the human side. And I wanted to talk a little bit about that. This is one of my first mentors. He was Thomas Tombrello. He was at Caltech. He was a physics professor there for many years. He was actually division chair of physics, math, and astronomy. So he's like their dean equivalent for about 10 years. But what I think was his most remarkable contribution to science was that he thought that you could take freshmen, it's a pretty radical idea actually, take freshmen, stick them in a seminar, and teach them how to do research. Which is a pretty crazy idea. Not only that you could teach students how to do research, but you could teach freshmen how to do that. So we learned a lot from Tombrello, and I sort of picked up from that. And today, my research group, this is us a few years ago, sort of carried that tradition on. And some of the results I'll show you a little bit later are the developments of the work that our students are doing in this. So let me show you a little bit about what one of these simulations looks like. This is what would happen if you took a little bubble, a bubble of hot nuclear fuel in the center of a star. And so we're sort of zooming in that hot bubble. So the bubble burns, it expands, and it's burning like a flame, but not like a flame. It's not a chemical flame, it's a nuclear flame, which is far more energetic. And because it's not ignited at the center of the star, it has buoyancy, like a bubble, like a hot air balloon in the Earth. It starts to rise. As it rises, this plume develops and becomes churning, turbulent bubble. As you can see here, it develops a huge amount of structure. That's kind of this process by which a star like this white dwarf can actually become disrupted. This is sort of a zoom in of that process on a small scale. Now, let me show you what that would look like if you put it in a real star. So I'm showing you two stars, and for the sake of time, in 20 minutes, I don't have time to blow them up separately, so I'm going to blow them up together. So what's shown here are these two stars, one on the left, one on the right. They're about on the same length scale, okay? So you're looking at the same length scale, same time scale. Time scale is a couple seconds. That bubble gets started, it starts to burn out, it erupts over the surface of the white dwarf. And if you look at the one on the left is actually evolving a little bit more quickly. The jet on the backside is where you should look, comes in, detonates the star, the white dwarf, and in the course of a few tenths of a second, it releases an amount of nuclear energy which is as great as our sun will in its whole lifespan. Now, the one on the right you see hasn't quite yet detonated. And what it turns out that this one, in a second or two it will, the fact that you can see it's expanded a little bit more means that actually it burns a little bit less than the one on the left, it turns out. So it's a little bit, turns out it will produce a different brightness supernovae. A little bit dimmer actually than the one on the left. And you can see here, right there is about the point of detonation. It detonates, it moves again through the star, disrupts the white dwarf. Now, that kind of line of investigation, the one on the left we published in a paper in 2008, the one on the right we published in a paper in 2012, kind of revealed that that story that we were telling ourselves for so long, that these kinds of white dwarfs, they go off with all the same intrinsic brightness everywhere, was not actually quite right. That in fact, this type of star could produce a wide range of outcomes, and that was very much against the conventional wisdom. In fact, we also showed in a second paper in 2012 that if you push that model a little bit further, you can actually get it to fail entirely. You can see here there's a white dwarf with this companion star, same picture, and what happened in this discovery, this is an observational paper that came out, is that people saw the shock signature of the companion star in that event. And it turned out that the shock companion was produced in an event which was dim, extremely dim, and it showed directly the connection between this type of model for producing these supernuclear supernovae and the fact that they're not the same. So you saw in that last frame there, the artist tried to show that the white dwarf actually survives an explosion, which was a remarkable, that's actually a remarkable result of the work that we did that predicted that the energy output is so low that the white dwarf actually survives an explosion, whereas previously people believed that the white dwarfs would always be completely disrupted. Okay, so there's an interesting product to this. So people tell themselves stories all the time, especially scientists. And the question really is, are the stories correct? Are they really true? So in 2011, there was a really remarkable event. This is called 2011 FE. Again, supernovae are categorized alphabetically. So this is the 161st event. You start with A, B, and so on. You go to FE. It's the 161st event that went off in 2011. And what was really remarkable about this event, it was the nearest, closest, and earliest supernova that was ever discovered. So the model that we just showed makes several concrete predictions. There should be a companion star. Companion star should be visible before the explosion. The companion star should survive the explosion, should be visible after the explosion. Also, something happens to the companion star. It's kind of like if you have a pumpkin and there's an explosion next to the pumpkin, you expect bits of the pumpkin to come out at you. You should expect bits of that companion star, which is mostly hydrogen, to come out. So all those predictions that there should be a companion star before the explosion, after the explosion, and hydrogen injected after the explosion were all spectacularly wrong. There is none of that in this supernova. So for the first time, people really started to question this basic model that people had had for so long. And so the alternative to this is what would happen if you took two white dwarfs, and this one we're showing here. This is an actual simulation. And what happens is the two white dwarfs can be driven together. The last few minutes of their life, they can become tidally disrupted. The same kind of tidal force that the moon exerts on the Earth and vice versa. But here, the tidal forces are intense because of the intense gravity of the white dwarf. And the companion star, the less massive of the two, the one which is more weakly bound, becomes tidally disrupted, completely shredded into a disk that surrounds the more massive, more tightly bound of the two. That's what you can see here. So my student Rahul, who's here, he worked on this and he studied what would happen if you took this and then asked the question, does this lead to a supernova? And there's a big question here. This is an outstanding question in the field. Does something like this, which observations seem to suggest should blow up, but do they actually? So here's what we're looking at. This is looking down on that disk, and that white dwarf that survives the explosion is the red spot in the center. So this is almost in real time. We're looking at this. So what you can see is that that disk of material evolves, forms a spiral, much like a spiral structure in a galaxy. And it's because that the center of mass of the system is not exactly on the central white dwarf. The central white dwarf is moving relative to the center of the system and produces the spiral structure. That spiral structure transports mass, transports angular momentum, we would say in physics, and causes an accretion of hot material to pile onto the white dwarf. And you can see right about here that actually goes off as a supernova. So sometimes, even though the simulations have lots of limitations, we don't put the whole universe in a box, we only model some parts of it, we only model some processes, but sometimes the simulation sort of transcends its own limitations, and that's when the discovery happens. And I have to say, one of the great pleasures I had was when I gave a talk on this in Chicago a couple years ago, and one of the long-standing members of the community, his name is Stan Muslim, sitting in the front row, and he's been around for 30 years. When he saw that, he just went, wow, right? Like, he'd been in the field for 30 years, never imagined you could blow up a white dwarf that way. And that's the power of scientific computing. So, I promised in a little epilogue to sort of tie this together. What's really the future here? And to tell you a little bit what maybe the future might hold here, I want to go a little bit back in the past. It turns out this whole picture about the expanding universe and our galaxy as one of many galaxies is actually not such an old idea at all. It turns out, if you go back to around 1920, people had an idea that we were probably in what people at that time called an island universe, or sometimes it was called back then they said even the word nebula. We were in a nebula universe. In other words, the Milky Way, what we say today, the Milky Way galaxy was the universe. And the reason was when you looked at telescopic images back then, you see stuff like this. There's some kind of blob of some kind of diffuse light there, which we know now to be a galaxy, but back then, that may have been just a cloud of gas in our own galaxy. It wasn't really clear. Turned out, that wasn't the correct idea at all, that we actually live in a universe of galaxies. This is a Hubble image of the Hubble Deep Field, and you could just stare at this image for days. It's so spectacular. You can see so many different galaxies. You can see gravitational lensing of galaxies. You can see stars in our own galaxy. There's a huge amount of structure, a huge amount of information in that single image. And it's very clear in that image that we live in a universe of galaxies. Now, in some ways, this debate is coming back in physics because, and as you might have heard, one of the big ideas in physics is that maybe we live in not just our own little universe, but we live in what's sometimes called a pocket universe or a bubble universe. We have this idea that the universe in its early stages was growing by enormous factors called inflation. But a remarkable thing about inflation is that if the current models are to be believed, once you get the ball rolling, it's hard to get this ball stopped. And so inflation keeps on going sort of everywhere. It's sometimes called internal inflation. And so you could have different pockets of inflation going on. The bubble that we live in happens to have the properties of the universe that we see simply because that's where we live. So there are some properties of the universe that are specific, like the value of dark energy in our little bubble of the universe. And what's interesting about this idea, it's very interesting, it's very speculative, and people tend to either love it or hate it. It's very polarimetric, very polarized topic. What's interesting about this is some people would say that it's untestable, but there is actually a very concrete test that you can ask for, and that is, it turns out all of these bubbles have to have a little bit of curvature in them. And that curvature has to be a very specific kind of curvature. You might have heard that there's some little corners of the internet are saying that the world is flat, and that's definitely not true. But the universe is nearly spatially flat. But the amazing thing is the prediction of the model is it can't be exactly flat. It has to have a little bit of curvature left over. And if the curvature is of the wrong sign, if you take two parallel lines and those two parallel lines converge, then the model is basically, the most popular model is basically ruled out. So in the next 10 years, people are measuring properties of the microwave background, it turns out, and with other information from supernovae, from other types of cosmological measurements, it may be possible to rule out or to have supporting evidence for this picture. It's such a wild and crazy picture, we're going to need a lot of evidence in support of it before people can actually believe it, and it would be great if we could rule it out if that's possible. So that's about all. I just want to leave with this one point. There's lots of questions out there. We don't know what dark energy is. We don't know what dark matter is. We don't know whether we're in a universe of ourselves, we're in a multiverse, what's going on. But there's a great quote by the great mathematician David Hilbert who said in this famous lecture in 1900 that actually you can judge the healthiness of a field by how many questions there are. And here's a field where there's a lot of questions, and if that's the standard, then I'd say it's quite a healthy field and an exciting time as well. Thank you very much.